let's talk about note card 10. Actually, I'm going to try to cover note cards 10 through 14. We're going to talk about the sine curve. We're going to talk about the cosine curve. And then we're going to talk about some transformations involving those curves. We're going to talk about the vertical stretch or shrink. And then we're going to talk about the vertical and horizontal shifts. Okay, so here we go. Let's talk about the sine curve. We have here a graph of the sine curve. And I will call this the parent sine curve because it's in its most basic form. This is just y equals sine theta, which means there's no shifts or stretches or anything going on with this curve at all. It's just your basic sine curve, and it has. Before I talk about some critical points, you're used to seeing this as the xy plane, but you can also see this as the theta y plane, or in other words, this independent axis can be the theta axis, because in this equation I have up here in this function y equals sine theta, the independent variable is theta, and so this would be the theta axis rather than the x axis. So get used to seeing theta or x there. And if you recall, we're going to be using, instead of degrees a lot of time, we're going to use radians. Since sine theta is a function that involves the sides of a right triangle, and it also involves angles, that's why we have our theta axis broken down in increments of pi halves here. And it can be broken down in different increments involving pi, but we will typically be using pi here, and we will be using fractions quite a bit. And so these values down here correspond straight below. So right here, this point over here, that's negative 2 pi. This point here is negative 3 pi halves. This point is negative pi. This point is negative pi halves. Obviously this is the origin, so that theta value or x value is 0. This point is pi halves, this point is pi, this point is 3 pi halves, and then this point over here at the end is 2 pi. Okay. We talked about periods and amplitude yesterday in note cards 8 and 9. The period of this function is 2 pi. We've got to look at what's the piece that's repeating. The piece that's repeating is this piece from here up, back through the x-axis, and then back up. This piece that I highlighted is identical to this piece that is unhighlighted. So this is the part that's repeating. And so to find the period, you have to find the distance along the x or the theta axis that that piece is repeating on. And so you should see that that's going to be from 0 all the way over here to 2 pi, so the period is 2 pi. Okay? Get used to using fractions. The range of this basic sine curve is negative 1 to 1. The lowest point is at y equals negative 1. The highest point is at y equals positive 1. It has odd symmetry. It has origin symmetry, which means it's an odd function. You could say it has odd symmetry. If you recall from the beginning of the year when we talked about origin symmetry or odd functions, is that when you look at this graph right side up, like we're looking at it now, if you take your note card and turn it over 180 degrees or rotate it 180 degrees, you'll see that it looks the exact same. That's origin symmetry, which means it's an odd function. And the x-intercepts are in increments of pi, and the y-intercept is 0. So the y-intercept is pretty easy to see. It's right there at y equals 0, and it's going to cross the x-axis at every increment of pi. So we've got negative 2 pi, negative pi, 0, pi, 2 pi, and if I kept going, 3 pi, 4 pi, and so on. I skipped over the domain. I didn't mean to. The domain is negative infinity to infinity. It's defined over the entire number line. or the entire x or theta axis. And those are some basics about the sine curve. You are going to have to sketch this, and I'll talk about some examples or some ideas of how to be able to sketch this parent curve, because when we graph these functions, if it's not your basic sine function, if it's maybe 2 sine then in parentheses theta minus 2, there's some transformations going on there with that, and in order to graph that sine function with those transformations, you would have to start out with this basic sine curve from 0 to 2 pi, and we'll talk about that in a second. Right now I want to introduce to you the cosine curve, and it has a lot of similarities. Again, we have the theta axis here, and that axis is broken down into increments of pi involving fractions here. More specifically, this one is broken down into increments of half pi. The domain is, again, all real numbers, negative infinity to infinity. The range is from -1 to 1. This function has y-axis symmetry. The y-axis is looking, it's acting like a mirror here. This piece looks like it's reflecting in the mirror, and it's over here. The x-intercepts are at values of pi halves, and the y-intercept is at 1. The period is still 2 pi because the piece that repeats is this U looking thing here, and it starts at 0 and it goes all the way over to 2 pi, so the period is 2 pi. So there are some similarities, and there are obviously some differences. They have different critical points, and we'll talk about those in just a second when we start to, well, actually might as well talk about it now a little bit. If I'm looking, when I want to graph these functions, and I'm trying to tie all these note cards together, and you'll know what I'm talking about more in a second. Before I can graph any variation of the cosine curve or the sine curve, I have to start off with the parent. And so you're going to have to be able to sketch this sine curve from memory. You're going to have to be able to sketch the cosine curve from memory. And so here's how I would help you to memorize how to actually graph the cosine curve. First of all, when you sketch either, you're just going to graph it from 0 to 2 pi. So I'm really, right now, I'm only focusing in on the positive side of this theta or x-axis here. So I'm only going to have to start with this piece. Now I'm going to have to include some negative values from time to time, because if I start off with this and I want to shift it horizontally left, that means it's going to end up over here on some negative values. But when I sketch this, I'm just going to sketch it this piece here, and it's pretty simple if you remember these critical points. Every y and x intercept are always going to be critical points, and every minimum and every maximum are going to be critical points. So these 5 dots here, these 5 points that I've highlighted, these would be the critical points that I would want to know about. And if you remember that cosine always starts at 0, 1, then it's going to go down in this U shape, and it's going to have an x-intercept at every half pi, so it's going to go through half pi. Then it's going to have a minimum down here at this point, pi comma -1. This value there is pi comma -1. Goes through there, then it's going to go back up through the x-intercept at the value 3 pi over 2. Again, it's a pi half increment, and then back up to 2 pi comma 1. And that's what you would have to start with before you would do any transformation or graph any other variation of sine or cosine. Let me go back really quick and show you how we would look at sine, how we would sketch that. Again, I'm only going to be interested in the sketching purposes anyway, of sine on this positive x or theta axis here. So I'm only interested in this piece from here in this area. And so the critical values to look at on this graph, again, is going to be every x-intercept and every max and every minimum that I see there. Those are my critical points that I'm concerned with. And if you remember for sine curve, that it starts out at the origin 0, 0, and then it goes up to this point pi halves comma 1, and then back through the x-axis, remembering that the sine curve has x-intercepts at increments of pi, and then down again to this value of 3 pi halves comma negative 1, and then back up again at this increment of pi at 2 pi. And so it's going to take a little practice because this is brand new to you, but you need to be able to sketch these two sine and cosine curves in this first little piece here in order to be able to do any transformations. Now let's talk about these transformations. The first shift that we're going to talk about is the vertical. Well, we're going to talk about stretch and shrink first. We talked about on note card 9 amplitude, and I did talk to you a little bit about amplitude, the amplitude of the function, of the trig function being this number out front of sine or cosine. Well, I'm going to define that here. If we have y equals a times sine x or y equals a times cosine x, a represents just this number, this constant, this scalar out here that's being multiplied by sine or cosine. And to graph this, first you would want to start off with that basic sine or cosine curve in that first piece that I was telling you about on that positive side from 0 to 2 pi. We'll define it that way, from 0 to 2 pi. First you would want to graph that, and then all you need to do is those critical values that I was telling you about, multiply every y value by a, and then map the point over, and you've got it. If a is negative, that means that it's also going to reflect or flip in the x-axis, but if a is negative, just multiply every y value by that negative value, and you'll take care of it all at one time. Now what I've said might be a little confusing, but when I show you these examples, it should be pretty easy. First off, in this first example, the thin line represents the parent or the basic function. So here our example is y equals 4 times sine x. So this thin line is sine x, and my critical points that I have are here at 0, 0, and then I have these critical points where it meets here at the max, then I have the x-intercept, and then again at this little minimum here, and then again at the x-intercept. And if I multiply those y values by a here, then I've got it, and that's all I've got to do. So the y value of this first point, this first ordered pair is 0, 0, it's the origin, the y value is 0, and so 4 times 0 is 0, that's why that one stayed there. So this one stays. The y value of this ordered pair is 1. 1 times 4 is 4, so this point maps up just 4 units up on the 4 on the y-axis, or 3 units up on the 4. The y value of this point is 0, that's why it stays there. The y value of this point is negative 1. Negative 1 times 4 takes me to negative 4, so I'm down here. The y value of this point is at 0, and 0 times 4 is 0, so it stays here. And so I would just trace this out on this bolded line here, and that's how I got this new sine curve with an amplitude of 4. Kind of a vertical stretch there. Example 2, I have a cosine curve, so the thin line is my parent cosine, but I have two things going on here. I'm having a stretch, but I'm also having a reflection or a flip in the x-axis. But if I take every y value of those critical points and multiply it by negative 2, it'll take care of both the stretch and the flip or reflection at the same time. So on this, remember my critical points are at the y-intercepts, the x-intercepts, and any minimum or maximum that I have on the curve. And I want to multiply the y value by this negative 2 out here. So the y value of this point is 1. 1 times negative 2 is negative 2. So that takes me down here to negative 2. It maps down here. The y value of this point is 0, and 0 times negative 2 is 0, so that's why that one stayed there. The y value of this point is negative 1. Negative 1 times negative 2 is positive 2, so that maps up here on the positive 2. The y value of this point is 0, and of course it stays there again. The y value of this point is 1, and 1 times negative 2 is negative 2, so it maps down here on the negative 2. Then we would have just traced this out. Now obviously these are already done for us, but I'm showing you how you would do them if it wasn't already done. And finally, my last example here, A is a fraction. And what we can recall from any other transformations that we've done, or vertical shrinks or stretches, if this number out front is greater than 1, then it's going to be a stretch. If this number out front is a fraction between 0 and 1, then it's going to be a shrink. And so here what we have, again, the thin curve is the original or the parent sine function. So I'm having to look at these critical values here that I've been talking about. And there's nothing like good practice and homework to make things perfect here. But when we multiply every y value by half here, this is what happens. 0 times half is 0. So hopefully it's obvious that that one stays there. 1 times 1/2 is half, so it maps down to the 1/2. This one is 0, stays there. Negative 1 times half is negative half, so it maps to the negative half on the y-axis. And again, this one's 0, and so that's how we ended up with this sine curve that was shrunk or flattened out a little bit. And so that's how you would do the vertical shrink or stretches, and that has to do with the number in front of either sine or cosine. Let's talk about the vertical shift. If we have a sine curve or a cosine curve, it's just like we've handled vertical shifts in the past. If we have a vertical shift, that's going to be this number that's out here. It's not going to be in parentheses with anything. It's going to be out here by itself, either added or subtracted, okay? So if we have a plus d value or some constant out here, or a minus d value, then it's, or this is a plus, I'm sorry, plus, and this is going to be a vertical shift up d units. Okay, if we have a minus, then it's going to be a vertical shift down d units. And so again, we start with the basic or the parent sine or cosine curve. This first example here is y equals sine x plus 2. So this thin line here is my basic one, and again, I'm looking at these critical values. These critical values from sine and cosine, when you trace or sketch this function over the domain 0 to 2 pi, these critical values aren't going to change, so you should be getting used to those. And this one is fairly easy. We have sine x, and outside the parentheses plus 2. That means it's a vertical shift up 2 units. So I just simply take each critical point and add 2 to each one, and it maps up 2 everywhere. And then I would sketch the new curve. Hopefully this is looking kind of easy for you here. This one is y is equal to cosine x minus 3. So again, outside the parentheses over here to the right, and it's minus, so it's going to be a vertical shift down. So I would take every critical value on the curve, the original curve, the parent curve, and I would just shift it down 3 units, and those just map 3 units straight down. And then I would trace that out. And that's how you would do a vertical shift. Now let's look at horizontal shift. Horizontal shift, it's a little different, but you're used to this because we've talked about this with quadratics. The horizontal shift is located inside the parentheses, and if it's a minus, then it's going to be the opposite. It's going to go right. If it's a plus, again, it's opposite, and it will go left. Okay? So the horizontal shifts for these trig functions act the same way as the horizontal shift for any other function, such as the quadratics we've talked about this year. It's going to be inside the parentheses, something added or subtracted to the independent variable inside the parentheses, and it acts in the opposite way. So if I look at these two examples that I have, I have here y equals sine, in parentheses, x minus pi. This means I have a horizontal shift right pi units. And don't let that trick you, because remember, we're going to be numbered here in pi units. Now, we have our original sine curve here, the thin one. I'm going to outline it in this color. And remember, my period of sine is 2 pi. So it starts at 0 pi, and then pi halves, and then pi, and 3 pi over 2, and then 2 pi. But I'm still looking at every critical point. And I just want to shift that or move it right 3 units. So I'm going to take pi units. So I take this value, and I want to move it right pi units. So this point goes to here. This point goes to here, pi units. This point goes to here, pi units. This point goes to here, pi units. And this one goes to here, pi units, giving me this boldened sine curve here. Okay, so you have to remember with these horizontal shifts that it's going to work as in the opposite manner. Okay. And finally, my last example here on this note card, I have y equals cosine, in parentheses, x plus pi halves. This means I have a left horizontal shift of pi halves units. And so, again, we're looking at these critical points, and it's okay that we're going left or right or whatever in these increments of pi, because our number line is going to be done in pi units. And so what I'm doing here is I'm going left pi over 2 units. So this point goes to here, this point goes to here, this point goes to here, and again from here to here is half pi. This point goes to here, and this point goes to here, giving me my boldened curve. So you're going to have to do a little practice on how to make your graph and set it up with your theta or x-axis being divided into units of pi.